The lengths of plane curves. Let C be a curve given parametrically by the equations x equals to f of t and y equals to g of t. T is bounded between a and b, or you can write t belongs to the closed interval a to b. So the question is, now that I have this piece of curve, how do I measure its length? Is there any easier way to measure the length of this curve? Okay. The best guess is using approximation. How do you use approximation to find the length of the curve? Well, the easiest way is to connect these 2 points and say, okay, the length of the curve is very close to the length of this line segment connecting these 2 points together. We're going to use Pythagorean theorem that you learned in algebra. So as you can see, we are using algebra a lot in this class. If you have 2 legs of a right triangle, like A and B, then the larger side or hypotenuse C follows the following relation. C squared is A squared plus B squared, or C can be written as the square root of A squared plus B squared. So basically, to find the length of this line segment, we're going to use Pythagorean theorem. On the horizontal line segment down here, the measure is delta x. Suppose this is x sub 1 and this is x sub 0, then delta x is x sub 1 minus x sub 0. Or in general, if you have x sub I and x sub I minus 1, we get delta x, which is the difference between the maximum value and the minimum value. With the same argument, you can find delta y, which is y sub 1 minus y sub 0. The difference between the maximum y value and the minimum y value. This helps us to calculate the length L using Pythagorean theorem. So let's go back to our line segment connecting these 2 points together, and let us call it L sub k, because eventually our goal is to divide up a curve into smaller line segments like L sub 0, L sub 1, L sub 2, and so on. So let us take a representative of these line segments like L sub k. Well, on the horizontal part, the difference between the maximum x value and the minimum x value can be represented by delta x sub k. And on vertical part, the difference between the maximum y value and the minimum y value can be represented by delta y sub k. We take p sub k to be f of tk and g of tk. Remember that x and y are both parametric with respect to t. And the smaller point, p sub k minus 1, is x and y, or f of t sub k minus 1, and g of t sub k minus 1. By the use of Pythagorean theorem, we know that the measurement for d is equal to the square root of x2 minus x1 to the second plus y2 minus y1 to the second. This is the distance between these 2 points, or as you remember, the hypotenuse for this right triangle. A in this case is your delta x, and the B in this case is your delta y. So D can be written as the square root of delta x squared plus delta y squared. So L sub k, or the length of this line segment, is the square root of delta x sub k to the second plus delta y sub k to the second, which can be written as the square root of, well, remember that your x is a function of t. So this is your larger x value, which is f of t sub k. And this guy on the left-hand side is your smaller x value, which is f of t sub k minus 1. So delta x sub k can be written as f of tk minus f of tk minus 1 plus delta y to the second, and the same argument, delta y sub k is the difference between g of tk and g of tk minus 1. So that's how you end up with g of tk minus g of tk minus 1. Since we are squaring this, we raise it to the second power. Now, if you have a curve in general, starting at the initial point p sub 0 and going to the terminal point like b, p sub n, to approximate the length of this curve, we can divide this into smaller line segments, connecting these points together. By the use of Pythagorean theorem and parametrization, we can find the length of this curve. So we're going to calculate each length and then add them all together. And eventually, if you have a lot of them, you're going to use summation and the Riemann sum, taking the limit. And as you remember from integral, you can define the definite integral to calculate the arc length. If delta tk is very small, the length lk is approximately the length of the arc pk minus 1 pk. So this is your arc. Now, by the mean value theorem, there are numbers like tk star and tk double star in the closed interval tk minus 1 and tk, such that delta x sub k can be written as the difference between f of tk and f of tk minus 1, which in turn is the derivative of that representative tk star, multiplied by the difference in tk. Very good. The same argument for the delta yk, which can be written as g of tk minus g of tk minus 1, which in turn is g prime of tk double star times delta tk. Very good. So remember that lk, which was the square root of delta xk squared plus delta yk squared. Now, if you add all of these small line segments together, we are basically defining the Riemann sum. This in turn can be written as, so here delta xk, which is f prime of tk star to the second. You're going to see what we're going to do with delta tk as well, plus delta yk, which is g prime tk double star to the second times the square root of delta squared tk, which gives you delta tk outside the radical. So we basically factored out delta tk squared, and the square root of delta tk squared is delta tk. So the length of the curve can be written as, when you take the limit, the definite integral between a to b of the square root of f prime of t squared plus g prime of t squared dt. So this is the formula and the argument and the discussion behind how we came up with this formula to calculate the length of a parametric curve. Now suppose you have a curve given by y equals to f of x on the closed interval a to b. This is the curve that is represented by y equals to f of x. We're going to do the exact same argument that we did. Here, we're going to approximate the length of the curve by a line segment which is in green. You find delta x, you find delta y, and you use the Pythagorean theorem to calculate this length. The length of the curve can be approximated by the summation of the square root of delta x squared plus delta y squared. In turns, if you factor out delta x squared, this is the square root of delta x squared parentheses 1 plus delta y divided by delta x, and the whole fraction goes to the second power. But please pay attention. Delta y divided by delta x is basically the rate of change. If you factor out the square root of delta x squared or separate these two radicals, the square root of delta x squared is just delta x. And by the mean value theorem, you know that you can write delta y divided by delta x as the derivative of a representative point like x sub k star. So far, we just added all of these small line segments together to find the length. And now, if you take the limit of this summation, the arc length follows the formula, the definite integral from a to b of the square root of 1 plus f prime of x to the second dx. So this is for y equals to f of x. And f needs to be has a continuous first derivative on the closed interval a to b. And this is the length of the curve between a and f of a to b and f of b. If you decide to write x in terms of y, or x is g of y, then you have to switch everything around. Where L is the definite integral c to d of square root of 1 plus g prime of y to the second dy. So it depends on how you deal with the function. You isolate y or you isolate x, you're going to apply these formulas. So let me summarize this for you and go over some examples. So if a curve like C is defined parametrically as x equals to f of t and y equals to g of t, as t is bounded between a and b, where f prime and g prime are both continuous and not zero at the same time on the closed interval a and b, and C is transferred exactly once, it just rotated once as t increases from a to b, then the length of this curve is the definite integral from a to b of the square root of f prime of t to the second plus g prime of t to the second dt. And if y is equal to f of x and function f has continuous first derivative on the closed interval a to b, the length of the curve from a and f of a to b and f of b is the definite integral from a to b of square root of 1 plus f prime of x to the second dx. And again, remember that if you decide to isolate your x and x is g of y, Then this length becomes the definite integral c to d of square root of 1 plus g prime of y dy. So sometimes calculating the integral this way is easier. Example for you. Question says, find the length of the curve f of x equals to x to power 3 over 2 when x is bounded between 0 and 4. So as you can see, y is equal to x to power 3 halves. This is the graph of this function between 0 and 4. The graph is increasing. Well, since f of x is equal to x to power 3 halves, f prime is 3 halves x to power a half. The arc length follows the formula definite integral a to b of square root of 1 plus f prime of x to the second dx. Now, L is the definite integral 0 to 4 of square root of 1 plus the derivative is 3 halves square root of x to the second dx, which in turns can be written as 0 to 4 of square root of 1 plus 9 over 4x dx. So we just took 3 halves square root of x and raised it to the second. We get 9 over 4 times x. To calculate this integral, we're going to use u sub. It becomes 4 over 9, the definite integral of 1 to 10. Why 1 to 10? Because u is 1 plus 9 over 4 times x, and du is 9 over 4 dx. So dx is 4 over 9 du. So your integral becomes the integral of square root of u du. But please note that when x is equal to 0, your u becomes 1 plus 0 or just 1, and when x is equal to 4, your u becomes, well, 1 plus 9 over 4 times 4, or u becomes 10. That's how you end up with these upper bound and lower bound, which in turns is 4 over 9, 2/3 u to power 3 halves from 1 to 10. Well, the number that you're getting is 8 over 27, 10 to power 3 divided by 2 minus 1. If you use a calculator, you get 9.1 unit. That is the length of the curve.